computational mathematics of biochemistry, and in particular with a main application being cancer research. And so I understand I'm a bit of a guest here in this conference in that regard, because I'm more really in the computational mathematics. But I would like to present this to you with the motivation that maybe there are some structures that interest you and could help to develop this field further. Also, why does it not click? Sorry. OK. So the main object of study are chemical reaction systems, and they are in principle relatively simple types of system at first sight. You have a pool of particles. Every concrete state is described as having a certain number of particles of each type. But then what makes this complicated is that a transition is, for example, take one particle of type A, take a particle of type B, take them out of the pool, put in a new particle of type C. H2 plus over H2 or something like this. And the problem is that the exact semantics of this is that you, first of all, you do each transition at a random time point in continuous time. And the parameters of how to choose this time point are dependent on the number of possibilities to realize this configuration you need for the input of the reaction at each point. So describing the dynamics of the system means finding the probability distribution over these possible configurations in continuous time, and that is a very, very hard mathematical problem. And I thought it would be a good idea to give like a rough idea of what's the state of the art here. So it was Max Delbrück, the Nobel Prize winner in physiology, who formulated this the equation which describes evolution in 1940. And sort of the heyday of this purely mathematical approach to this was in the 60s, when some applied mathematicians found, for example, that certain orthogonal polynomials can be used as eigenbases to solve this problem. But somehow the long and short of it is that, I mean, to this day, there are very few systems of interest which can be really solved, let's say, exactly, where you can really give the full probability distribution. And I found it very interesting that in this community there is, for example, work of Behr, Fong, and Spivak, which focus on a certain interesting approximation of the system, which is so-called deterministic rate equation, which describes the evolution of the approximate concentrations of these particles, which is a good approximation for chemical industry applications where you have large copy numbers. But unfortunately, this particular approximation doesn't work for biological systems. And we know this in part due to this immense work. So in the 70s, there was an algorithm developed by Gillespie called the stochastic simulation algorithm. And it's an algorithm, so you do not produce a probability distribution, but you produce individual trajectories of the system. And then if you take enough of those, you can sort of get an idea about the properties of the probability distribution. And there was an incredible amount of work done on this, and many of the empirical means of knowledge we have come from these sort of numerical experiments. But if you go to biochemistry, and my main motivation is cancer research, the problem even becomes harder, because now not only do you have all this problem with this time evolution in probability space, but on top biological molecules have structure. Proteins, there are some macromolecules which can, on top of just reacting, they can stick together, they can form macrostructures. And so a typical system, and for example a signaling pathway in biology, so this is a simple metabolic pathway, but if you have a signaling pathway, you could have 10 to the 33 would be a typical number of individual types of particles. For each, then you have a concentration, and you can imagine this goes through the roof in terms of complexity very easily. But what's interesting is now, so what do biologists do? Biologists are very, very clever at finding good approximation and abstraction of such system. And it is the state of the art is to talk about pathways in these systems. And a pathway is something like, it's sort of a causal account. You don't even try to get the full probability distribution, but you try to reason about, so can the system produce a certain sequence of events? Let's say to produce a rare, interesting molecule. And if it can you compare these possibilities? And then can you maybe reason about some bigger properties of the system based upon these pathways? And believe it or not, this is very possible. And that is sort of the main machinery behind systems biology and especially cancer research. And the funny thing for me is I'm a mathematical physicist, now working in computer science, but so there's a large field in what I would think would be applied category theory, but I mean debatable, which is like called categorical graph writing. It's a 40-year-long history, but it seems to be very disjoint from this community, I would say. But it's from this background that developed the modern state-of-the-art ansatz to formulate biological systems. So any competitive simulator of biochemical reaction systems nowadays is based upon a certain type of rewriting system. It's either the version developed by my colleague Vincent Danos in 2003, Or it's a version on, funnily enough, organic biological molecules can be written as a formula, which is an abstraction, but I mean, and you can directly do transformation on those, and there's an interesting school on doing these types of rewriting. I'm more in the community of biochemistry. And so what I will show you today is what I hope is a very good, it's a development in semantics of these systems, which is about what are pathways. The weird thing is, even after 80 years of history, this is not exactly like a mathematical concept. It is some empirical concept. It's something well defined on individual traces. But I will show you that there's a sort of abstract object which might interest you, I hope. I mean, that's basically the take-home message of this talk. And OK, so my task is not easy because I have to tell you, and I mean, I have probably 10 minutes for this. So how does rewriting work? And then, I mean, why is this good? So, I mean, what you will like, I think, is that there's a very nice description of rewriting based upon adhesive categories. And an adhesive category is essentially a good generalization of sets in a way. So you have push-outs along monomorphisms, you have all pullbacks, and you have a property called the Van Kampen property. But that has a very simple interpretation, as that you can have a meaningful idea about what is a sub-object. A sub-object is essentially described as having a monomorphism into another object. And this property essentially says that this works the way you think it should. And then there should be, we need an initial object to play the role of sort of the empty configuration. And we need on top finitarity. So it's a property saying that there's at maximum finitely many monomorphisms into any object. That's a property you can put. And then, of course, classical representatives of these are all sorts of, well, finite sets, finite graphs, and then these more complex objects like biological molecules as well. Okay, so and then, I mean, I have this slide only to show you that there's an intuition behind this. Is very easy, which is that a push-out really describes, so in sets it would be the sort of abstraction of union of two sets along a common intersection. And for graphical objects, it's the exact same thing. That's what adhesivity does for you. For example, if you have two graphs and they have a common sub-object, which is a vertex, you can glue them together. That's one part of the rewriting machinery. Then there's something called push-out complement, which is a